Welcome back to the course on superconductivity. Today we're going to talk about the boiling heat transfer curve. We'll first go over the definition of the entropy, and then define the sensible heat and the latent heat. We'll finish with the boiling curve of water and then see the typical boiling curve. First of all, the word entropy was defined by Rudolf Clausius in 1865. Most of the time it is explained as the variable that measures the disorder, which is the classical explanation, or the uncertainty, the statistical definition. Entropy is a property that only depends on a system's internal state variables. So referring to the temperature, the phase, etc., it is defined as the energy divided by the temperature. The specific entropy is the same definition divided by the mass. Mathematically, the change in entropy is defined as an infinitesimal amount of heat supplied to the system, divided by the temperature at which it occurred. Entropy's usual behavior versus temperature is described on the right-hand side graph. We can see that the entropy of a material increases steadily with the temperature until a phase change where there is a discontinuity. This discontinuity is explained by the fact that phase transitions require energy, but occurs at constant temperature. In other words, heat is supplied, but the material's temperature does not change until it has accumulated enough energy to undergo a change of state. Also, entropy is quite hard to understand, so don't worry about not understanding its meaning right now. A concept closely related to what we just saw is the sensible heat and the latent heat. The sensible heat is the heat exchanged to increase the temperature of a material to a certain temperature, depending on its mass. The specific heat capacity describes how much energy must be supplied to raise the temperature of 1 kilogram of a material by 1 degree. This applies only when there is no phase transition. When a phase transition occurs, we use the latent heat. It is the heat exchanged to change an amount of material from one phase to another. The specific latent heat is the heat exchanged for 1 kilogram of that material to undergo a phase transition. On the left-hand side graph, we can see is the phenomenon we talked about on the previous slide. Heat is supplied and the material heat up until a phase transition occurs where heat is still supplied but the temperature does not change. When using a wet cooling system, the cooling is due to the latent heat, therefore the system is maintained around the boiling temperature of the liquid. For instance, nitrogen is widely used for HTS and its boiling point at ambient pressure is around 77 K. However, while this tells us the amount of heat that can be taken away, it does not tell us the cooling power. On a boiling heat transfer curve, this information is referenced versus the difference in temperature between the object to be cooled and the boiling temperature of the liquid. Typically, there is 4 regions. The first one, where the difference in temperature is small, is the natural convection. Here no bubbles are seen and the liquid just moves due to the heat. Then, there is the nucleate region where bubbles form more and more violently. After reaching a maximum in heat transfer flux, we reach the transition region that ends where we reach the film boiling at this minimum. Film boiling happens when there is a huge difference in temperature. This can be seen when a drop of water seems to hover over a hot pan, or in this case when a hot ball of metal is submerged in water. A film of gas is formed around the object, lowering the heat transfer. If we increase further the temperature difference, the heat transfer flux will eventually reach the maximum heat transfer of the nucleate region, but keep in mind that the graph is logarithmic, so this will happen at a very high difference. The boiling curve heat transfer curve has for most liquid this kind of behavior, so we usually define delta T peak, the temperature difference where the heat transfer reaches its maximum value in the nucleate area, QPK, the peak heat transfer flux at that point, QFM, the minimum heat flux in the film region. On the table below, these points are referenced for several cryogenics. To conclude, the boiling heat transfer curve tells designers the cooling power of a cryogenic, depending on the temperature difference between the system and the coolant. This tool helps designers to choose the appropriate coolant and design for their heat exchanger or system.